Okay, welcome to 12.2, moving charges in a magnetic field. There is a formula with this, and what it is F is equal to Q V B, perpendicular. Now, this F stands for the force that the charge will experience, and we put that in newtons. Q stands for the charge, and that's measured in coulombs. V stands for the velocity at which it's moving, standard units meters per second, and B is the magnetic field strength. And the units for magnetic field strength is in Teslas. Now, if you take a look at this formula, you'll notice this little upside down T, and that stands for perpendicular. In fact, all of these things, the force, velocity, and magnetic field strength, they are all vectors, and this formula has it going in perpendicular to each other, which means that the velocity, magnetic field, and force are all at 90 degrees to each other. Now, really, if you were to take a look, this would actually be F is equal to Q V B sine theta, which is how the angles are to one another. This is not on your formula sheet and is beyond what we're going to be doing within our particular course. But this does lead us to the three-finger rule, because you've got three vectors, force, velocity, and magnetic field strength, and they're all perpendicular to each other. We use our hands to show this, where the thumb represents the velocity. Kind of like when if you're trying to hitchhike a ride, you would stick out your thumb and the cars would vroom past you. And that's how I remember V is the velocity. And it is also your thumb. Pointer finger is the magnetic field strength. Now, this is if you were to put a magnet here, the way that the north end of the compass would point. So if you had the compass sitting here, the north end would be pointing this way. And so this being the pointer finger, if you remember when you're a little kid and you would go bang, 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 that's how I remember the pointer finger is B, bang. Now, the third finger is the middle finger, and this represents the force. Now, I have racked my brain about this and cannot figure out how to figure out the force is the middle finger. You're gonna have to come up with that on your own. You also notice that we do have two hands, and we have two charges, positive and negative. We use the left hand for negative charges, left hand negative charges, and we use the right hand for positive charges. So what this all means is that if a charged particle moves in a magnetic field, it will experience a force in really neither direction. And what that does is the free moving charge within that magnetic field will in fact bend or turn in the direction of the force, which obviously alters the direction of the velocity, which is going to then alter the direction of the force. We're going to watch a quick little video to kind of explain what's going on with this. Let me get that centered here.
Can you see this particle of charge Q?
Now let's consider that this particle is moving in a uniform magnetic field B. Now as you can see, the direction of the magnetic field is perpendicular to the velocity of the particle. So no work is done, and also there is no change in the magnitude of the velocity, but the direction of momentum of the charge will change. The perpendicular force QVB
QVB means force.
acts as a centripetal force and therefore produces a circular motion perpendicular to the magnetic field. So the particle will describe a circle if V and B, I'm repeating, V and B are perpendicular to each other. Now consider for a moment that the particle has a velocity component along the magnetic field. Now what will happen? Well, the parallel component remains unchanged, as the motion along the magnetic field will not be affected by the magnetic field. But the motion in the perpendicular direction, that is perpendicular to B, will describe a circle, as in the previous case, don't forget. So the particle will have linear motion along the magnetic field and also circular motion perpendicular to the magnetic field. So what can you say? Well, the path of the charge will be a helix.
Okay, let's take a look at an example here. Example number 1, we're looking for the force is equal to QVB. We're looking for what is the velocity. So we're looking for the velocity of an alpha particle. Alpha particles have a charge of positive 3.2 times 10 to the negative 19 coulombs. We can figure that out through our formula sheet. It's traveling through a magnetic field that's going 4.20 Teslas to the north, and it experiences a force that's moving to the east. So we're looking for the velocity. So we're going to divide both sides by QB to get the velocity. That force, 4.83 times 10 to the negative 13 newtons, divided by 3.2 times 10 to the negative 19 coulombs, and a magnetic field of 4.2 Teslas will equal the velocity. And so you wind up with a velocity of 3.6 times 10 to the 5 meters per second. However, because velocity is a vector, we need a direction. So it's a little bit hard to show on here, but we're going to try our best. With the compass needle, we know that the magnetic field is pointing north. Right? We're told magnetic field is going in a north direction. And so your pointer finger is going to be lining up here. Which pointer finger, you might be asking? Well, it's going to be your right-handed pointer finger. And the reason is because what you're seeing is that alpha particle is positive, right hand positive. You're then going to put your middle finger along here in the east direction. So if your right hand has a pointer finger pointed north and your middle finger pointed east, you're going to see your thumb pointed straight down. So the thumb is going into the page. Now, if we pretended that this was actually on a map, this means that this particle, this alpha particle that is experiencing a force east when it was in a magnetic field going north, actually was traveling straight down. And so the velocity at that point was in fact down into the ground. If you're having some difficulty understanding that, please pause the video, ask it. I will definitely help you through that. Okay, our next one. Ions with a charge of +1 and a mass of 8.12 times 10 to the negative 26 kilograms travel perpendicular through a region with a magnetic field of 0.15 teslas and a speed of 8 times 10 to the 4 meters per second. First of all, we're going to determine the magnitude of force acting on it, and then the radius of curvature that we saw. So, we're looking for the force, QVB. The charge of +1 means 1.6 times 10 to the negative 19 coulombs, traveling at a velocity of 8 times 10 to the 4 meters per second, with a magnetic field strength of 0.15 teslas. And so the force is going to be 1.92 times 10 to the negative 15 newtons. If we want to figure out the radius of curvature, as we saw in the video, this is going to wind up spinning in a circle. And so the centripetal force, which we've actually already found, is equal to mv squared over r. We want to find the radius, so mv squared over the force. We've got the mass of 8.12 times 10 to the negative 26 kilograms. The velocity we've already used, and we do have, being 8.00 times 10 to the 4, squared, all divided by the force, which is what we've already calculated to be 1.92 times 10 to the negative 15 newtons. And so the radius, when you calculate all that, make sure you square your velocity, which is a common mistake. You wind up with 0.27 meters, or 27 centimeters, is the radius of this path. I would like you to give this next one a try. Pause the video. Give it a try. See how you do. Taking QVB, multiplying proton has a charge of 1.6 times 10 to the negative 19 coulombs, times the velocity times the magnetic field. You should have got an answer of 2.35 times 10 to the negative 18 newtons. Because we were just looking for the magnitude, we do not need to worry about the direction in this case. Try this next one. Pause the video and give this next one a try. Okay, so if you've got running along the surface of the equator, it means the magnetic field would be pointing straight north. It's running west-east, so that's your velocity, and so your thumb is pointing towards east, pointing finger towards the north. You're using your left hand because it is negative, which means that the middle finger is pointing into the page or into the ground. Taking a look at example number 3. We've got a carbon ion with a mass of 2.01 times 10 to the negative 26 kilograms and a positive charge with a magnitude of 1.6 times 10 to the negative 19. So we've got the mass, we've got the charge, enters an external region magnetic field with that as shown here. And we want to find the perpendicular speed at which it's deflecting. And will travel in a straight line. And it's traveling in a straight line because it's balancing with the gravitational force, meaning that the force of gravity has to equal that deflecting force. Okay, So what we've got is mg is equal to qvb. And what we're looking for is the velocity, the speed. So we're going to take mg divided by qb to find that v. That mass of 2.01 times 10 to the negative 26 kilograms. Gravity, we're assuming we're near the Earth, so 9.81. Divided by the charge, which is 1.6 times 10 to the negative 19 coulombs, and the magnetic field strength of 6.32 times 10 to the negative 5 will equal the velocity. And so that winds up calculating to, you wind up with a velocity of 0.019 meters per second, or 1.9 times 10 to the negative 2 meters per second for the velocity. Okay. Give this next one a try. Pause the video, give it a try. Okay. Again, you're equating the force of gravity with the force that is keeping up. It's a magnetic force that is equal to the force of gravity. And when you equate those two, so the force is mg, you've got q, you've got b, what you find is it doesn't take a very fast moving particle in order to maintain this. 1.11 times 10 to the negative 6 meters per second. You'll notice that with both the questions, and the main reason why that is that electrons do tend to deflect out of our way. They're not usually just hanging about at the same level, because they are in fact so light that just a tiny bit of force moves them quite a bit. Anyway, it's time to work on your questions. If you've got any questions, please let me know. Thanks for watching.